Edge computing. Edge computing is a distributed computing paradigm which brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. The origins of edge computing lie in content delivery networks that were created in the late 1990s to serve web and video content from edge servers that were deployed close to users. In the early 2000s, these networks evolved to host applications and application components at the edge servers, resulting in the first commercial edge computing services that hosted applications such as dealer locators, shopping carts, real-time data aggregators, and ad insertion engines. Modern edge computing significantly extends this approach through virtualization technology that makes it easier to deploy and run a wider range of applications on the edge servers. The increase of IoT devices at the edge of the network is producing a massive amount of data to be computed at data centers, pushing network bandwidth requirements to the limit. Despite the improvements in network technology, data centers cannot guarantee acceptable transfer rates and response times, which could be a critical requirement for many applications. Privacy and security. The distributed nature of this paradigm introduces a shift in security schemes used in cloud computing. Not only should data be encrypted, but different encryption mechanisms should be adopted, since data may transit between different distributed nodes connected through the internet before eventually reaching the cloud. Edge nodes may also be resource-constrained devices, limiting the choice in terms of security methods. Scalability in a distributed network must face different issues. First, it must take into account the heterogeneity of the devices, having different performance and energy constraints, the highly dynamic condition, and the reliability of the connections, compared to the more robust infrastructure of cloud data centers. Reliability management of failovers is crucial in order to maintain a service alive. If a single node goes down and is unreachable, users should still be able to access a service without interruptions. Moreover, edge computing systems must provide actions to recover from a failure and alerting the user about the incident. To this aim, each device must maintain the network topology of the entire distributed system so that detection of errors and recovery become easily applicable. Speed. Edge computing brings analytical computational resources close to the end users and therefore helps to speed up the communication speed. A well-designed edge platform would significantly outperform a traditional cloud-based system. Efficiency. Due to the proximity of the analytical resources to the end users, sophisticated analytical tools and artificial intelligence tools can run on the edge of the system. This placement at the edge helps to increase operational efficiency and brings lots of advantages to the system. Edge application services reduce the volumes of data that must be moved, the consequent traffic, and the distance that data must travel. That provides lower latency and reduces transmission costs. Computation offloading. For real-time applications, such as facial recognition algorithms, showed considerable improvements in response times, as demonstrated in early research. Further research showed that using resource-rich machines called cloudlets near mobile users, which offer services typically found in the cloud, provided improvements in execution time when some of the tasks are offloaded to the edge node. On the other hand, offloading every task may result in a slowdown due to transfer times between devices and nodes, so depending on the workload, an optimal configuration can be defined. Please subscribe, like video, share, comment, and click bell icon for upcoming videos.